Okay, so the class I'm doing today is basic in two senses. So it's basic in that it's simpler than the classes that will follow, and it's basic that all these things I'm presenting today are building blocks for the later classes. So for example, I will talk about the perceptron, which is a building block for neural networks. I will talk about optimization techniques, which are used in the same kind of way, just for more complex models. I will talk about tricks and of the trade of convex optimization, non-convex optimization, which are used again for the more complex models. So if you listen to my class, you will learn something that is also useful later on. And on the other hand, basic means I want to introduce you to machine learning for those who have never heard about machine learning. So a view of machine learning that might be not influenced from what the papers write about artificial intelligence and I don't know what else. So what I will talk today about, the first model we will look at is we are trying to model the frog's perceptual system. So we are trying to build a machine learning model of the frog's view of the world. So you can look at this as artificial intelligence, but well, how intelligent is that? It is not very intelligent because biologists found out in the 1950s that the frog's vision is basically built up out of 4 basic detectors. So one is a contrast detector. So is there something, is there a sharp boundary? Then the second one is how big is this object that I can identify with my contrast detection? So is it convex, or how convex is it? Then does the object move, and how fast does the object move? So that's how the frog sees the world. So he doesn't see any colors. He doesn't have an appreciation for art or beauty. He doesn't, that's how we see it, right? So maybe he has a way of appreciating the beauty of other frogs, but with those 4 detectors, it's quite hard, right? Must be some other way he does that. So the frog's goal using those 4 detectors is to feed himself, to capture any object of the size of an insect or worm, providing it moves like one. So some objects move faster and are smaller, some objects are bigger and they move slower, but so he wants to detect the right objects. So now our goal is to build a model of this system and learn to capture the right objects. And learning means we have a set of training data, and what we want to do is we want to predict for an unseen object, is this an object that we can eat or not? So learning always means we want to generalize from our training data to unseen data. So then we have learned something. So now you can, if you look at this example I'm using here and the setup where you have training data that tell you those objects are in the left, on the left side are inedible, label minus, and on the right side they are edible, label plus, and features. So we are only using 2 features here, namely how big is the object and how fast is the object. Then you can imagine, well, does the frog really learn how to feed himself in this way? Does he have supervised training data that tell him this is edible and this is not edible? Probably not. But this is one of the basic assumptions for all machine learning. Even for the most advanced classes, you will hear supervised learning. You have given training data that are featurized in a way and have labels. So this is pattern recognition. People call it artificial intelligence now, whatever. Yeah. So let's try to learn a model of edible and inedible objects from those data. So I'm proposing a model that has the following parameters, namely the probability of label plus, edible, probability of label minus, inedible, and then probabilities of all possible feature combinations given the object. So we have a probability of convex equals small given inedible. Probability of convex equals medium given inedible, and so on and so forth, right? So does anybody have an idea how we could learn from these data what those probabilities are? So what would you say? What is the probability of plus, of edible, given those data? Yeah?
Just
Frequency? Yeah, but give me a number.
So it's 5 or it's 6 over 8 for convex.
6 over 14, right? So how? So you're summing up all of the labels, right? Make
So like in the second slide.
So what is it now?
Here that convex equals small.
Yeah,
Addition. The object is not edible.
yeah. Okay, now, but let's start with probability of plus, right? That's 6 out of 14, and the other one minus is 8 out of 14. Yeah. Then say again, probability of convex equals small.
So 8.
Do we have 6 over 8, right? We have 6 times convex equals small over 8 negative labels, and so on. Convex equals medium, so we count medium. This would be how much? This is just an example. This is the data. So I want to show you how a supervised machine learner would approach to learn the frog's perceptual system. So if he wants to learn for an unseen object, is it edible or not edible? One would have to have labels that tell you for a particular feature view of the world, is it edible or not? Then you learn the parameters and are given a certain model and use these parameters to predict. Yeah. So some of you had the intuition that we just do relative frequency counts, and this is what we do. So I will explain to you in very much mathematical detail how we get to this model and how we get to these frequency estimates. This is just, but it's intuitive as well. So 6 out of 14, 8 out of 14, 6 out of 8, and so on and so on. Then what we want to do now, and now this is what really is machine learning. We don't want to just replicate our training data. We want to say something about an unseen object. So now we want to see what if our object is medium convex and medium fast. So we have never seen this combination in our training data, right? How do we do it? Our model predicts that we just multiply the probability of a negative label with the probability of medium convex given negative, also not inedible, and probability of medium speed. And those parameters we have, we can combine them and make a prediction. And the same way for the positive label. Yeah? What's the probability of being edible and the probability of this feature combination given an edible object. And what we see is one is 0.027 and the other one 0.024. So our prediction would be, since the probability of being inedible is larger than the probability of being edible, we predict it's not edible. So this is an end-to-end use of a machine learning model on data, and we do a prediction on unseen data. So, given this example, so what I want to tell you basically is that what machine learning in essence does, machine learning can be seen as a problem of function estimation, where the function is, in the models I'm talking about, they are called models, and the models are some combination of feature representations. So we start from feature representations. So the feature representation for the frog was these 4 detectors, like convexity, contrast, speed, and so on. And then machine learning means we take this model and we set up some error function or some objective function, and we optimize the parameters by fitting the model to the training data. That's what we did by doing these relative frequency counts. So the frog uses, he doesn't, but we are assuming he uses binary classification into edible, inedible objects as supervision signals for learning. So a machine learner who models the frog's perceptual system would do this. So the model we used to modeling the frog's perceptual system is called naive Bayes. We will shortly learn about it. It's a linear model, so all the models I'm talking about in this lecture are linear models, and the learning is done by convex optimization. So let's, again, an outline. So what will I talk about? I will talk about naive Bayes, so the model that we used for the frog. I will talk about more complex models, logistic regression, which is a standard model in statistics, but it has been adopted in natural language processing under different names. Then we will talk about the perceptron, which is also very close to logistic regression, naive Bayes, and large margin learners. Before, I will talk a little bit about feature representations that are used in natural language processing, so that you have an intuition beyond the frog's worldview of what features can look like and how it makes sense, this linear combination of features, what could it look like, how is it integrated in natural language processing applications. And then I will talk about very general techniques that are applicable not just to linear models, but to any kind of models like regularization, online learning, and a quick outlook at how nonlinearity can be introduced into the linear models without giving up the convex optimization routines. Okay. So the notation I'm using throughout the lecture is I'm using X's for inputs. So the 4 features the frog had were x1, x2, x3, x4, so the 4 components of a 4-dimensional feature vector. Or in a natural language processing application, it could be words, right? So all the words in the lexicon are features. Then the outputs in natural language processing, there can be many, many different kinds of outputs. There can be classes, it can be binary, or it can be structured outputs like translations or parse trees as outputs, and they are denoted by Y. And the feature representations are mostly joint feature representations, so they are functions of inputs and outputs. So for example, if you look at a translation model, then a feature representation always knows about the source and the target. So a feature representation is something like a translation of a word in the source language into a word in the target language. So you have to know both. So it's not just an input feature representation, it's input and output together. Or a parse tree. A parse tree knows the sentence and it knows the partial tree. Okay. So common ranges of feature representations. This is not really important, but common ranges are counts or binary ranges. So if you take real valued features and you bin them, so you say this in an interval from value x to value y is one bin. So if the value falls into that bin, I say 1, otherwise I say 0. This is one way of simplifying the model, or they can be continuous. So we can work with all kinds of features, but I could do a whole lecture on feature extraction and feature modeling, what binning actually does. It's a nonlinear transformation, and how you should pre-process your data before you do any machine learning by different kinds of scaling, linear scaling, and Z-score transformations, and so on and so forth. There are nice textbooks about this, but we'll just assume that we have some in the most general case, real valued features. Okay, example, text classification. A feature representation for text classification in a joint feature map would be something like phi sub I sub j from of x and y is 1 if x, our input, contains the word interest. So if we have the word interest in the text, and y is the class financial, and 0 otherwise. So and we would assume that if we integrate this feature into a model, then it would get a positive weight because interest is a positive indicator of the class financial. So for part of speech tagging, we could have a feature representation like the input has to be bank, and the part of speech tag is verb. So what do you think? What weight would it get, positive or negative, for standard training data, standard texts? Negative, right? But definitely not a high positive weight, because bank normally is not a verb but a noun, right? But it has this meaning, and we will talk about it later. In some data sets that are used in natural language processing, bank never appears in this meaning verb. So you will have a data sparsity problem, an overfitting problem to this particular data set, and you have to do something about it. Then named entity recognition. So the goal here is to identify texts, so parts of texts, and classify them into, for example, the named entity person or named entity object or building. And what you do is, so this will come, you will see this construction. It's called the Kessler construction later on. So what you do is you build a multiclass classification problem into your feature vector by reserving parts of your feature vector for all the classes that you want to classify. So for example, as we see, so we have 8 features here from 0 to 7. And the first part, the first 4 are reserved for the classification into the named entity person, and the second 4 are reserved for classification into a named entity object, right? And so the feature just says, does it contain George with the named entity meaning or named entity label person? And you see the very same George with object, but now it's the first feature of the second partition. And so you can basically do named and multi-class classification with a standard model that has a joint feature map. So we will always use joint feature maps, and joint feature maps are very useful and general and can be used for multi-class or binary classification as well. So they are called block feature vectors. Yeah, equal size blocks of the feature vectors correspond to one label. Then another example, machine translation, that showcases this particular necessity of having a joint feature map. Namely, so if a feature tells you about a phrase translation, so the French y-a-t-il, so one feature is set to 1 or 0 if y-a-t-il is present in the source and it's translated in are there in the target, or if it's translated in are there any. So that's a real example from a statistical machine translation models from several years ago. And what would you say? Which phrase indicator should preferred? Y-a-t-il to are there or y-a-t-il to are there any? What is more frequent? Yeah? Yeah. So are there Well, sometimes, so the old style machine translation models, they extract phrases from the, so multi-word expressions, consecutive words, and sometimes it was useful to have non-meaningful phrases, so to say, non-linguistic phrases in the translations. And the linguistically meaningful translation would be "are there," but sometimes "are there any" is a good phrase as well, but it's not as frequent as the other one. So if you look in the old style machine translation models in the phrase tables, you will see a lot of phrases that don't make sense. But if you just throw them out, you will suffer badly in performance because you need them as well. All right, so last example, parsing. So in parsing, the label Y consists of a whole tree, and the input consists of a sentence. And the feature vector, for example, if you have a context tree parse, consists, for example, of the rules that make up the tree. And the label includes the sentence as well. So it's somehow a little bit a convoluted feature representation, but I just wanted to show you a few examples of this notation X and Y. It can be very many things. Translations, so strings, sequences, trees, or just labels, like, or categorical labels from 10 classes or 2 classes. So what we want to do now is we want to learn a discriminant function that is a linear combination of features and weights. So what we want to learn in our function approximation setup, so we want to learn f of x and w, and what we want to do at test time, we want to predict the best label y by just taking the argmax under our linear combination of features and weights, and assuming we have the optimal feature, the optimal weight vector learned. So now machine learning consists of 2 parts. We have to talk about models. So what are different kinds of linear models, and then how do we learn the weights? So just a reminder, so the simplest way of thinking of this is multiclass classification, right? So your output is just one of n classes, and you want to classify your input into one of n classes. So the example we had in the beginning was for the frog, it was 2 classes, edible, non-edible. And for the binary classification case, so all of the textbooks on machine learning up to, say, 10 years ago, they basically were written for binary classification, because for binary classification and for binarized feature vectors, everything can, so from a mathematical point of view, everything is easier. You can visualize things very nicely. For example, you can visualize what you're learning with machine learning as you're learning a hyperplane. So hyperplane is a plane in n-1 dimensional space that separates your positive from your negative instances. So this is the goal of machine learning for binary classification. And it's a little bit harder to visualize this for the multiclass case. So let's say we have 3 classes, plus, minus, and 0, or cross and circle and dash, right? And so the visual is what we visualize now is this the partition of the crosses are all points where the argmax of our discriminant function, of the linear discriminant function, gives us the cross as the right label, and so on for the others. Yeah? This one?
Is it correct that for each pair of classes we have different weight vectors?
No, we have that's the point. We have one weight vector that we learn in our Kessler construction, our block feature vector that can be used for all of them.
So it's got straight with like one line
So what you do is you take your input and you look in the partitions of your vector and you find out which partition of the vector gives you the maximal weight. And then you classify it into that partition.
Well, but in this case, there is no partition.
Well, I mean, you can think of it as one versus the rest. Then it's a binary classification, right? The crosses versus all the others, or the circles versus the others. And so you can build up these partitions one by one. Yeah. Okay. So now we know what our models are, our functions. They are linear functions. And now we want to learn the weights. So the nice thing about having these linear functions is that the weights can learn by convex optimization. And convex optimization is still the mainstream of mathematical optimization. And there is a lot of work on non-convex optimization, but for example, if you later on learn about neural networks, what people do, they just throw the techniques of convex optimization at a non-convex optimization problem and hope that it will turn out right. Yeah? So it's not, there are no specialized techniques used for taking account of the non-convexity. Oh, there are tricks and heuristics, but it's not like something completely different is done. But here, for the linear models, we can use convex optimization, and we have all the guarantees that the mathematical framework of convex optimization tells us, namely that we can find the optimum, and we know how fast we can find the optimum. So, okay, so what do we start out in convex optimization? So we start out with training data, which we assume are independently and identically distributed, so it's called IID. So this is one of the assumptions that is always wrong in natural language processing, because let's say we do machine translation and our training data are sentences, consecutive sentences in a text. They are never independent of each other, right? Or if you partition images from the same domain, they are also not independent. Or videos, video frames. It's just, but it doesn't matter. So it still works, even if we make this wrong independency assumption. Okay, so we start from IID data and a feature representation. And what we want to do is we want to optimize our weight vector in this linear combination. And how do we do that? We have to set up an objective function that we maximize or minimize by just minimizing the negative of the objective, of the positive objective. Okay, the objective functions. Now, for supervised learning, in the best case, the objective functions decompose over the training data. So the objective function is just a sum over the objective functions for this the single training data. Over objective function, let's call it a loss function. So for each training data pair x, y, we incur a loss, and the overall loss for our training set is the sum of the losses of the individual training examples. So the loss function is a function that measures the error that we make if the parameter setting, if the for W is not really correct. So if it doesn't really represent the training data. So as you can see, the setup, the convex optimization or the optimization setup is really just, it's not a machine learning setup, it's a optimization setup. So we want to optimize an objective on the training data. And then where machine learning comes in basically is in making sure that what we learn on the training data also applies to unseen data. This whole business of generalization. How can we make sure that we are not just overfit on the training data, but also learn something on unseen data? So, but the basic, so in that sense, machine learning is a weird field because it combines two frameworks that have different objectives. One is optimizing on the training data, which is not what you really want in machine learning. The other one is talking about something that you can't really quantify because you don't know about the unseen data because they are unseen, right? So you have to know about the whole distribution of training data. So it's there are two competing fields, and there's not very much work that tries to combine those two fields. And those are the most interesting papers, I think, that really try to figure out from a principle point of view, how can you ensure generalization capabilities of your machine learning algorithms, not just do an experiment and get good results and yeah. Okay, an example for an objective function would be the 0-1 loss function. So that's the classical objective function for binary classification. So what it is, for each example, the loss is defined as loss is 1 if our prediction times the label is less or equal than 0. So for binary classification, what that means is if the label is positive, then the prediction has to be positive as well. If the label is negative, then the prediction has to be negative as well. Otherwise, we incur an error. If we make the right prediction, no error. So this is a step function. So this is this function here, right? Can you read that? So it says y times f of x. This is exactly what we had here, right? So if y times f of x, so the label times the prediction is negative, we have a loss of 1, otherwise we have a loss of 0. So this would be the ideal objective function to optimize in binary classification. Unfortunately, well, let's look at the definition of convexity first, then I ask my question. So what we want to do is we want to apply convex optimization, so our objective functions have to be convex functions. Convex means, that's the definition of convexities. Now, so the x's and y's here are not the same x's and y's that we used before. I'm just using the same notation because I stole this image from a textbook and I can't fiddle around with the PDF. So you have to think about the x and y as our weight vectors, w and w prime. Yeah? It's just a general definition for functions. So what it means is a function is convex if the graph of the function lies on or below the line segment connecting any 2 points on the graph, right? So it's always, if you connect any 2 points, the graph of the function is always on or below. So that function has one global minimum. So my question now is, if you imagine this step function, the 0-1 loss step function, is this a convex loss function? No? Why not? So where is this condition not satisfied?
No, because there is a global
So if you think let's go here. If you do a line segment from here to here, then the condition that we had above definitely is not satisfied, right? Because the graph of the function sometimes is above the line segment. So it's not convex. So this is why what we do in multiclass or binary classification, we are looking at convex upper bounds on the 0-1 loss. And all of these convex upper bounds here, so they are called, so this green one is called hinge loss, and this one is the perceptron loss, and this one the log loss, the red one. they basically correspond to algorithms. So we will look at 3 algorithms in the following. One is the perceptron. This has a particular kind of loss, and the algorithm basically just is a particular way of optimizing this convex upper bound on the 0-1 loss. And the support vector machine corresponds to the hinge loss, to the green one. And logistic regression corresponds to optimizing the log loss, the red one. So optimizing an upper bound, minimizing an upper bound is a good idea, because if you can't basically go wrong, right? I mean, you can't go wrong very much. So what you do is here, when you have 0 error, some of those functions, and that's how the intuition is different between, let's say, perceptron, hinge loss, and log loss. They penalize correctly classified examples differently. So the 0-1 loss has a 0 loss, right, if you do a correct classification. But some of the other losses, they penalize, if you are not exactly correct, then you also get a little bit of a penalty. So you incur a little bit of a loss if you don't do exactly the right thing. The perceptron doesn't. The perceptron only looks at right or wrong. The hinge loss penalizes, and the log loss penalizes as well. And then what they also do differently, if you have an error, the error is also penalized more heavily in the log loss. It's an exponential curve than in the hinge loss and in the perceptron loss, which is a linear. So a linear penalty on errors, and the one is an exponential, or even worse for the other, the squared hinge loss and modified Huber loss. So there's, if you look at different algorithms, so the first thing for algorithms is always, you think, what do I actually want to optimize? I'm setting up an objective function, and the objective function has particular properties. It implements a particular error, and it penalizes correct classifications a little bit, and it penalizes incorrect classifications in different ways. And then I'm applying techniques of convex optimization to these convex losses and get an algorithm. So the algorithms, mostly, they don't appear from nothing. They are derived from loss functions by application of techniques of convex optimization. That's at least the way I want to introduce the algorithms. So 2 words on convex optimization. So I can't do a full class on convex optimization, so we will look at 2 different ways. One is unconstrained optimization. That's the easy one. So what we want to do is we want to minimize an objective function. What we have to do is we have to compute the gradient, so the vector of partial derivatives, and we do a stepwise gradient descent procedure where we follow the negative direction of the gradient until we find the point where the gradient of our function is 0. And for convex functions, we know this is the global minimum. It's not a saddle point, it's not a local minimum, this is it. And then a more complicated case is constrained optimization, so that we will have this case right away in the naive Bayes case. So it's what we have a function, and we want to find the minimum of the function on a particular constrained surface. And the constrained surface, let's say the constraints are named G. Then there's a particular technique, it's called Lagrange multipliers, and the Lagrange multiplier technique, what it does is you can show that the gradient of the function lies in a plane perpendicular to the plane that is spanned by the constraints. So this here is a plane that's spanned by the gradients of the constraints. So at the minimum of the function under the constraints, what you have to find is the point where the gradient of the function and the gradients of the side conditions are in one plane. And using this construction, you can just set up a so-called Lagrangian. You just set this equation to 0 by taking the right-hand side onto the left-hand side, subtracting the right-hand side. And then what you have is, if you optimize this function for x and alpha, then you have an unconstrained optimization problem. So you can make a constrained optimization problem into an unconstrained optimization problem by folding in the constraints. So this is one of the techniques that you, if you don't know this, then you should look it up in a convex optimization textbook, because it will appear more often in machine learning. People don't talk about it in papers because they assume you know it. If you don't know it, then look it up. Yeah, it's not very hard to understand. One of the books that is I can really recommend to understand those things, if you're not a mathematician, is the textbook by Steve Abney. So it has a weird title. It's called Semi-Supervised Learning for Natural Language Processing, but it's a nice introduction to machine learning in general for natural language processing from scratch. So he doesn't make any assumptions. So he explains everything. And if you have read this book, you will have understood convex optimization, Lagrange multipliers, and all the linear and nonlinear models. All right, so let's get started with naive Bayes. So now we know what models are, we know what constrained optimization and unconstrained optimization is. Now we can derive this algorithm that we used in the beginning for modeling the frog's perceptual system from a mathematical point of view. So we can set up the model, we can set up the objective function, we can use constrained optimization to get at these relative frequency estimates. So the relative frequency estimates are not just intuitively correct, but they are the fallout of applying convex optimization to this particular kind of model. So the model that we are using in naive Bayes, it's a probabilistic model. So we want to, the discriminant model is the conditional probability of label given input. And using Bayes rules, we can turn this around because the probability of input is the same for all labels. So we can just cancel it, yeah, if we do the argmax. And what's important, the model is a generative model because what we are actually modeling is a joint probability of x and y. So the advantage of this model is, of a generative model, is you are not you cannot only apply it for predicting the best label, but you can also turn it around and synthesize data, for example. You can assign probability to XY pair, so you can generate synthetic data and visualize the data and see by this visualization, does the model make sense? This is one advantage of a generative model. The other models we will look at are not generative, but they are discriminative models, so they make one more assumption that makes the optimization easier, but you're losing this property of being able to turn the model around. Okay, so why is naive Bayes called naive Bayes? Because we are making a conditional independence assumption. So the conditional independence assumption means that the probability of the joint feature representation, so the probability of all features, feature 1 up to feature m given label, is just the probability of the features given the label. So this is an independency assumption that is naive in a sense, right? Because it's not true. So how would the model look like if you wouldn't make this independency assumption? What would the probability of phi 1 to phi m given y be if you just apply the rules of probability? You learned that yesterday. I'm sure you learned it. Yeah? So it's the chain rule of probabilities, right? So for every feature, for feature 5, you would condition on feature 1, 2, 3, 4. For feature 6, on feature 1, 1, 2, 5, and so on. And so what you make in this naive or independence assumption, you say, all the history, I don't care. And this is obviously not true, right? For example, if the features are words in a lexicon, they are not independent of each other. But this, the nice thing about making this independency assumption is that what you get in doing the convex optimization is you get an estimate, an algorithm that is very, very simple. So it's very efficient. And in the old times of machine learning, so if you look at, most of you might never have seen this book because it's from the 1990s, from Eugene Charniak, Statistical Methods for Natural Language Processing. So it's a 100-page book. It introduces all the old techniques like hidden Markov models, probabilistic context-free grammars, and so on and so forth. And all of these models in the 1990s, they made this independency assumption. And the nice thing about them were they had a really nice closed form solution for estimation that allowed you to just take counts from corpora. No iterative modeling. No week-long waiting until your one GPU server is finally done with your neural network. You can just, in a day, you have all the estimates. This was, yeah, the old times. So naive Bayes, we have the model. Now we want to do learning. We have to figure out what are the parameters that we want to learn and what is the objective function. So our inputs are XY pairs. We have a feature representation. Like for text classification, it's words. For the frog examples, it was these 4 feature detectors. And the parameters is probability of label and probability of feature given label. And the objective function, the classical objective function that is still used for other models is maximum likelihood estimation. So what we want to do is we want to maximize the probability of our training data. So it's the likelihood term. So what it means is maximum probability of training data. The likelihood is just to make clear that it's not actually a probability what you're estimating, because what you're mostly doing is you're optimizing, as you will see on the next note. What you're mostly doing, you're optimizing the log probability, yeah, because it makes things easier in optimization. So, but that's our objective. And I show you the solution on the next slide, and then we derive the solution. So what we want to find is the parameters that optimize the probability of our training data given our naive Bayes model with this conditional independency assumption. And what we see is, what we will find out is the optimal parameters for the label probability is just the relative frequency of the label. So these double brackets mean the number of instances where label YT equals a particular label. So where a gold standard label equals a label. And this is the instances of feature instantiations in the training data. So this is exactly what we did when we calculated the probabilities of labels and features for the frog, right? We did relative frequencies. And how do we get to these relative frequencies? We take our objective function, rewrite it a little bit, and use the technique of Lagrange multipliers. So the rewriting is done by taking the log. So instead of the probability of labels and feature probabilities, we have sums of log probabilities, and we can divide the problem into 2 problems, one argmax problem for the label probabilities, one argmax problem for the feature probabilities. And we'll see that both of those problems have the same form, so we can simplify the derivation a little bit. So the form is basically, we want to find the parameters P that maximize a term that says we have a sum over events where we count, we have a count of the event and the log of the probability of the event. And we have constraints, side constraints. And the side constraint is that our parameters, P of the events, are probabilities. So they have to sum up to 1 and be greater or equal than 0. So what we have is a constrained optimization problem. This is our objective function. And if our P parameters are linear, then this whole function is a convex function, and we have side constraints. So what we do is we apply the technique of Lagrange multipliers to this and derive the optimal values. So the Lagrangian for this objective with constraints looks like this. We just introduce Lagrange multipliers lambda. For this one constraint, we have only one constraint, namely that the probability of event, that the P function is a probability, so it sums up to 1. And the standard form of constraints is the constraint has to be equal to 0, so the sum over V, P of V minus 1 is 0. So this is how we fold in the side constraint into our objective. Then we can do constraint optimization of this objective. So the derivative with respect to P of V, that's easy. So what we have is we have to take the derivative of something that is behind a log. So that means we have to 1 over that something, like PV. And then we take the derivative. And the derivative of P of V is 1 times count of V. And for the right-hand side, the derivative is 1, the rest is constant, times lambda. So this is the derivative of this objective with respect to PV. Then we have to do the derivative with respect to, normally we would have to do the derivative with respect to lambda, right, in order to find the global solution. But that's the nice thing about this model. Making this independency assumption gives us a closed form solution. So closed form solution means we can express the lambda in terms of the other terms in our equation. So the lambda can be, it dissolves. So it's a closed form. So we don't have to compute the lambda iteratively. So how do we do this? We now, since we have computed the derivative with respect to PV, we set this to 0 because what we want to find is the point where the derivative is 0, right? That's the point where the global minimum lies, right? You see that? How to set this to 0? Count V divided by PV set to 0 is exactly this term here. And then we make use of the fact that the P function is a probability, so it sums up to 1. So basically what we do is we sum the left-hand side up over V, and we get 1 here. We sum up the right-hand side over V. What we get here is the count of V summed up over 1, and then we get that lambda can be expressed as the sum over V count of V. So this is how we get to this relative frequency estimate. By just doing Lagrangian constrained optimization and making use of the fact that we have a probability distribution here, and since the model makes an independency assumption, it turns out that our derivative allows us to get a closed form for lambda, and we can express our probability estimate just in terms of counts. So all we have to do in terms of estimating the probabilities of this naive Bayes model is counting events in the training data and normalizing. So we count events of labels, count events of features, and so on. So and this technique has been used for 20, 30 years in natural language processing for different kinds of models, hidden Markov models, context-free grammars, for parsing, for all kinds of applications. And it was always, the nice fact was, you could just count the probabilities from corpora. And then at some point people thought, well, these models are not expressive enough. We don't want to make this independency assumption. And as soon as you don't make this independency assumption, you have to move to more complex models where you can't make this, where you can't get a closed form solution, and you have to use iterative techniques. And this is what we do now. But it has been done in the 90s as well. And the next models we look at, logistic regression is one of these models that in our field came about as an alternative to these models that make this independency assumption. So the logistic regression models, they have been around in statistics for a long time, and you can find them in any statistics book, and they're used for different purposes. But in our field, they came about as more complex, more powerful models for the same kinds of applications, and with the only negative side effect that you have, all of a sudden you have to do real machine learning. You have to do iterative algorithms, and you have to wait until your algorithm converges, and you have to think about convergence, and where did you converge at, and so on. Here it was very clear. You do the counts give you the optimal parameters. They maximize this log likelihood of your training data. All right. So there's one slide that just explains you how to see the naive Bayes model as a linear model. You just take the log of the probabilities, then you arrive at the form that looks very much like the linear model that we had before, where you have a weight vector and a feature vector. And that's one of the other reasons why naive Bayes and those types of models are out of fashion now, because they have a really unfortunate way of dealing with unseen data. So let's look at this example. That's our training set for text classification. The features are words, and we have two classes, sports and politics, and the features are hockey is fast, politicians talk and fast again, Washington and sleazy. Now we want to do classification of a new document, Washington hockey is fast. So what's the probability of Washington hockey is fast for class sports and for class politics? Yeah, it's going to be higher for sports. Why? Well, no, I don't think that's right. So how is the model computed? It takes the relative frequencies and multiplies them, right? So what happens to a word that has never been, to a feature? A word is a feature that has never been seen in the training data. Like Washington for sports. We have never seen Washington and sports. So that feature will be 0. So if we multiply this feature in, which we have to do in our model, what will we end up with the probability of the class for this feature? 0, yeah? And the same for the other one. We have never seen hockey in politics. This will also be 0. So both of them will be 0. Doesn't make any sense at all, right? So what we have to do for those kinds of models, and this was a whole industry, so-called smoothing techniques. So we have to make sure that 0 events are not hitting the model so hard that you can't say anything about unseen data anymore. So the simplest way of doing it is you're just adding a little factor to every count right from the start. So you floor each count with a small number, like you floor it at 1 or some other number. And this can be explained in a Bayesian framework, but never mind. I mean, this is what you have to do. But this is one of the big advantages. So the model, it looks nice. It's a clear maximum likelihood application, a convex optimization problem, but it has some pitfalls that you have to work around. And the discriminative models that came about in the 1990s or in the 2000s, they don't have this problem. They are more expressive, and what they do is they make a simplifying assumption that proved to be very useful for applications. Namely, so the simplifying assumption is just applying Occam's razor, which means among competing hypotheses, the one with the fewest assumptions should be selected. And if you have the choice between modeling a joint probability and a conditional probability, if you are at test time only needing the conditional probability, you shouldn't model the joint, but you should model the conditional, and doing away with all of the advantages of the generative model of the joint probability. So just model the conditional. And so that's what the models we will look at in the following all do. Logistic regression does maximum likelihood estimation of a conditional probability, not the joint. And the perceptron and the support vector machine, they minimize the classification error. They minimize exactly the error that you want to minimize for your application at test time. So they don't do anything more involved. And why don't they have the smoothing problem? Because the models, they have a normalization constant that unfortunately doesn't allow this closed form solution anymore, but the normalization constant makes sure that all the probabilities, they never will floor to 0. They will always be backed up by other features. So we will see what this model looks like immediately. But this is just a disclaimer why, I mean, nowadays nobody would say it's a good idea to use naive Bayes anymore, because the advantages that naive Bayes has, namely the ease of computation, the ease of estimation, they are not worth the losses you have in making all this independency assumption and the smoothing problem. So now the discriminative models are, or the models that minimize a particular error, are the models to use. And one of the first models that we look at is logistic regression. Okay. So logistic regression, it has been invented in different fields under different names, and you might have heard other names. So one of the names that was very popular in the 2000s in our field was maximum entropy models. It's the very same model. It's just another explanation of why you set up this model. Then in vision, the fields were called Markov random fields. It's also the same model. Then in neural networks, early neural networks, they used Gibbs models. And the Gibbs distribution is exactly the same distribution as the logistic regression model. Then in statistics or mathematics, people called just looking at the form of the distribution, it's an exponential distribution, so it also has been called exponential model. And then other people look at more like from an optimization point of view, they call it log linear model, because they see if you take the log of this model, then you have a linear model, and you are now all of a sudden again in this nice framework of linear or convex optimization. So it's all the same, right? And it was really like a fashion. 5 years it was called like this, and then the next 5 years you called it like that, and then the other. It's logistic regression. It's a linear model, namely like this. It's you exponentiate this linear function, this linear combination of weights and features, and you take a normalization constant that ensures that your model is a probability distribution. And this model is more powerful than the naive Bayes model, where you make an independency assumption. In the naive Bayes model, the normalization constant would be 1, right? So it basically falls out. But here in this model, you can have arbitrary features. They are they're not necessarily independent. They can be overlapping. They can be long-range features. And by using this normalization constant, you can always ensure that your model is a proper probability. You don't have to care about the features being independent so that you can take the product. By definition, the product is only correct for a joint probability if the events are independent of each other, right? So in the old model, you always had to take care of independence. But now you don't have to do that anymore, since you have this normalization constant. But the normalization constant, as we will see, you can't use the old style algorithms anymore. If you take the derivative of the maximum likelihood estimate of the objective here, then you will see there is no closed form. You have to have an iterative algorithm. So, but it's still a linear model, right? In the end, if we want to, at test time, we want to find the most probable label, the normalization constant cancels out, and the argmax of the exponent is just the same as the argmax of the linear combination of features and weights. So how do we learn the weights? Again, we do maximum likelihood estimation. So we maximize the likelihood of the training data. So the product of the conditional probabilities of labels given inputs is the same as maximizing the log likelihood. This is the same idea as before. So we want to maximize the probability of the training data. The nice thing is you can see very easily that this function here is concave. So it's the opposite of convex, because we formalized it here as a maximization problem. And so how can you see that? Because if you take the log of this probability, what you end up with is you have the log of the numerator, is log e of the linear function, so that's a linear function, minus log of the denominator, and the denominator is log some exponent, which is also a convex function. So we have a linear function minus log some exponent, which is also a convex function. In the end, you have a convex function, or concave function. So we don't find a global a closed form solution, but in the beginning, several techniques have been used to optimize this kind of models. They were called iterative scaling, improved iterative scaling. Then people use conjugate gradient techniques. And now people use stochastic gradient ascent or stochastic gradient descent techniques. So it took a while to figure out what the best optimization techniques are for this kind of models. And the early work tried to make advantage of knowing what kind of function you have. You have an exponential function, and for exponential functions, they have certain properties, maybe some algorithms that are fit to optimize exponential functions work better, but what we found out in the end is just applying the best general purpose optimization techniques like stochastic gradient descent works best also for these functions, and that's what we do nowadays. So gradient ascent, what it means is you optimize your function by taking steps into the direction of the steepest ascent of your function. So you take a step into the direction of the gradient. And gradient descent is just the opposite. You take a step in the negative direction of your gradient. So you do convex optimization. So gradient ascent for this kind of model, for the logistic regression model, looks like this. Until convergence, you update your parameter vector W by adding to the parameter vector from the step before a multiple of the gradient of your loss function. The multiple is signified by alpha, so this is the learning rate. So it tells you how far do you want to go in this direction of the gradient, how trustworthy is the gradient, step size or learning rate. So all we have to do now in the rest of the lecture to get at algorithms, we have our model set up a maximum likelihood objective function or some other error-based objective function, and we have to calculate the gradient. So the gradient is the vector of partial derivatives. And what you can show, although you don't have to show it, and it has been shown in the convex optimization literature, if you have a convex loss function, then this kind of gradient ascent or gradient descent steps will give you the global maximum or the global minimum. And you can also show how fast you will arrive at the global maximum or global minimum. So how do we minimize this problem? We just minimize the negative of this, right? So what we do is L is now redefined as the negative log likelihood, and this is what we will use in the rest of the chapter, the negative log likelihood, and we minimize this. And then we take a negative step in the direction of the gradient. Okay, let's derive the gradient for this logistic regression objective. It's not that hard, and it's quite instructive because even with neural networks, you are using functions that are very similar to the loss function for logistic regression. So for example, the softmax looks very much like a logistic regression function if you want to understand how you arrive at the gradient. If at all you are interested, if you not just trust TensorFlow and the automatic gradient computation, if you want to derive the gradient yourself, here in this lecture, the gradients are all derived step by step. So the loss function is the log probability defined as this exponentiated linear function divided by a normalization constant. So if we take the derivative of this, so in the second line, what we do is the derivative of a sum is the sum of the derivatives. Then we take the log of this of the denominator and the numerator separately. So we have minus log of the numerator plus log of the denominator, and we can split the derivative for the numerator and the denominator. And taking the derivative of the numerator, it's minus log of something. So first of all, 1 divided by something is this here. Then the derivative of e up to the something is e up to the something times the derivative of the inner, right? E up to the something. And the derivative of our linear function is just a feature. So the derivative of sum over j, wj times phi j gives us, if we take the derivative with phi I, gives us phi I. Okay. So what we end up with, since we have the same term in the numerator and denominator, we end up with minus phi I of xt yt as the derivative of the numerator. Yeah? And then we do the same for the denominator. So we have to take the derivative of log normalization constant. So the log normalization constant is log over sum over all outputs of E up to the linear function. So again, the derivative of log something is derivative of 1 over something times the inner. So this is 1 over something times the inner. The inner is a sum over derivatives of E up to the something. So it's a sum over E up to the something times the inner. And the inner we had before, the derivative of the inner, like for the linear function, is phi I of xt y. And this time, we can't cancel out the terms because they are in a sum. But what we get is, if we are summing up the linear function and dividing it by a sum over the linear function over all outputs, we get the probability distribution, right? So what we get here is an expectation of the feature value. So what we have in the end, the gradient of the logistic regression model has this form here. And what it tells us, in order to find the optimal parameters for this logistic regression objective, if we do a minimization, so this term will be minimal if we put all the weight on the phi i's for xt, yt. So the features as they are in the training data, this is what we are interested in, and they have to be equal to the expected feature values. So in order to so let me phrase it differently. When is this derivative 0? This is where we have our global minimum. It's 0 at the point where the left-hand side term, also the term, the minus sum over t phi I term is equal to the right? And when are they equal? When we set the parameter weights, the probabilities, so as to give the same estimated probabilities to our features in the model as they are in the training data. So we basically mimic the frequency counts in our training data. So we set the parameter weights to get an expectation, to calculate an expectation of the feature values as they are in the training data. So the model is basically told to mirror the training data by giving putting out expectations for feature values as they are provided in the training data. And we can be sure, since this model is a convex function, that if we train long enough, that we will find this minimum. It's another question if it's a good idea to actually find this minimum. But, well, this is how it is. OK, so to summarize, logistic regression, what we do is we define a model, which is our conditional probability. We define an objective, which is our negative log likelihood. And we apply gradient descent to the vector of partial derivatives, which is defined like this. But this is it. This is all. This is what's behind Gibbs models, log linear models, exponential models, maximum entropy models, whatever. This is what you do. There's a typo? Yeah, thanks. OK. So I'm a little bit too slow, but I think we should do the perceptron, and then we take a break, because after the perceptron, you will have forgotten a lot of stuff, and the perceptron is a good point to end because it's probably the algorithm you will remember best in the later lectures, and it's a quite simple and nice algorithm. So what the perceptron does in difference to logistic regression and naive Bayes, it's optimizing an error function directly. And the perceptron, it's one of the few algorithms that we will discuss that has been invented independently from my claimed framework of how machine learning algorithms have to be developed. Like, first you have an objective, and then you take convex optimization to it, and you derive the algorithm. The perceptron has been invented really only based on intuition, and the intuition for the perceptron algorithm was what we want to do is we want to figure out for the examples where we make an error, we want to update our weight vector in a way that for the examples, like in line 4, we make a prediction, take the argmax of our linear model, and if the argmax is not equal to our gold standard training data, then we make an error, and what we do is we update our weight vector by moving the weight vector in the direction of the feature representation of the gold standard and away from the feature representation of that example that we erroneously put as prediction, where we erroneously predicted that this would be the correct example. So this is the intuition behind the perceptron. Just let's do an algorithm that basically adjusts the weight vector according to whether we make an error or not. The weight vector is just running after the errors that we are making. And then let's show that this algorithm actually converges. Converging meaning that the algorithm converges to a bounded error, so that the error gets smaller and smaller. And the convergence proof for the perceptron is very instructive because it's quite simple, and if you want to understand convergence proofs for different kinds of machine learning approaches, then they are all very, very similar to the perceptron proof. So they make a certain assumption that every step of your algorithm shrinks the distance of your estimate to the true estimate, to the global minimum. And this is what the perceptron proof also does. It shows that with every step you are getting somewhere that is bounded, that is the error gets smaller and smaller. And if we have a look at this perceptron learning algorithm at the convergence proof, then you will not only have seen objective functions and constrained optimization, you will also have seen at least one proof for how these algorithms actually work and that they actually do what they are supposed to do, that they are converging to something useful. Okay, so in order to do this proof, we have to make one little assumption. So the assumption in equation 1, which means the training data is separable with margin gamma. So separable with margin gamma means that the training data is easy enough so that we can always find a weight vector that does this separation. Let's think about it in terms of binary classification, so that the linear score that we give to the gold standard example, xt, yt, is always greater than the linear score that we give to all other examples by a margin of gamma. So we classify, or we give a score to the correct example that is higher than all the other examples by a certain margin, by a certain positive margin. So that's an assumption that we have to make. Then we can show convergence of the algorithm. So we work with training data that for which this condition holds. Then we can show that our algorithm actually converges after a finite number of steps to such a weight vector. Okay, So one question, so just to check if you're still awake, why do we require that the norm of u here has to be 1? Why can't we just assume an arbitrary weight vector u? Say louder, please. Again, right, yeah. Because if I multiply u by a constant greater than 0, like alpha, beta, then I can then the margin is increased trivially. We want to avoid that. So we have to make a certain condition that lets us not find this trivial solution, right? Okay, so the convergence theorem, what it says is, if we assume that our feature vectors are of size r, so our feature vectors are always this difference vectors of gold standard versus prediction feature vector. So we only have, so the norm of the feature vector is of size r. Then the number of mistakes during training is bounded by r squared divided by gamma squared. So what this means is, if we use a very, very rich feature representation, like 10 billion word features, or words and part of speeches, and whatever, and whatever, and whatever, then the error will be larger, right? Because it's smaller than r squared. So why is that? Because if we have a very expressive model, then the error on how should I say that? The perceptual algorithm, you have to remember the perceptual algorithm. That's one of the nice things about the perceptual algorithm. The perceptual algorithm is not training, is not optimizing a criterion on the training data. It's always making a prediction on unseen data. So what we do is we run through our data, we make a argmax prediction, and then we make the prediction on the next training datum that we haven't seen. So the perceptual algorithm is an algorithm that does adjustment of its parameters online, so on the fly. So when we talk about mistakes that are made during training, those mistakes, they tell us actually something about errors on unseen data, because every time we make we do a check, do we make a mistake or not, we do it on a training data that we haven't seen before. So ideally, the perceptual algorithm is run on an infinite stream of training data. So we're not actually running over the training data in cycles or epochs, but ideally, and this is how the proof is formalized initially, on an infinite stream. So what it means, mistakes made during training are bounded by r squared. So if the model is more expressive, then we are overfitting to the data that we have seen before. So we are making actually more mistakes. But the most important thing, it's inverse into gamma squared. So if the margin is larger, then we are making less mistakes. So it's important to classify the training data or the data that we have seen before in our sequence with a big margin, because then the number of mistakes will be smaller. So now let's show how we can prove this. So we have the perceptual algorithm on the left-hand side. And what we want to show is, so it's just one slide where we have a little bit of derivations, like we have to go through this slide. And we are showing a lower bound and an upper bound. And every step is really simple. But those steps, those are the steps that are, so I just recently did a proof for an algorithm for a non-convex optimization algorithm, and I was surprised how similar the steps I had to do to give this proof are to the perceptual algorithm. So the steps are, we are making use of our update rule, and we are making use of the assumption number 1 that we had before. So the separability by a margin. So what we are doing is, we are assuming that the weights at step k minus 1 are weights before we make the case error. So the case error is made at example xt, yt. So error means we are making an argmax prediction y prime, which is not yt, which is our gold standard. And then we're making an update, right? So our weight vector wk is updated as wk minus 1 plus this difference of feature vectors. We go in the direction of the positive of the gold standard example and away from the prediction. Now what we do is we multiply the left-hand side and the right-hand side by our weight vector u. This is what we have here. Do I have something now? Doesn't work. Yeah, in the first line, we just have the left-hand side times u and the right-hand side times u. Then we can, the term before the greater or equal sign can be cancelled because this is greater or equal to gamma, as we just said before in our assumption, right? So we can say that this whole term is greater or equal to u times w up to k minus 1 plus gamma, right? Because this, the term u times feature representation of gold standard minus feature representation of prediction is greater than gamma, yeah? Then by induction, we can say that for all k, u times w up to the k is greater or equal times k times gamma, right? Because it's we have this this relation of u times wk is greater or equal than u times wk minus 1 plus gamma k times. Yeah. Thanks. I don't see it. Yeah. Okay, now the last line. So that's the only line where you have to apply some of the well-known inequalities that are mostly used in proofs like that, like the Cauchy-Schwarz inequality. The Cauchy-Schwarz inequality just tells us that every dot product is upper bounded by the norm of the components of the dot product. Yeah, it's the same as the triangle inequality. We just use that. I'm not explaining it. If we use this and apply it to our result after the induction, that what we see is since the norm of u is 1, we get again by that the norm of the weight vector is greater or equal than k times gamma. So it was the only difficult step maybe was the Cauchy-Schwarz inequality. If you want to do this proof on your own, then you have to think, how can I bound this here? How can I make use of the facts that I have? And one of the facts is that the norm of u is 1, so I have to have the norm of u somewhere in my proof, and then it cancels out. And yeah, so this is what we have. Then the upper bound, so we come from the other side. What we do is we expand the norm of wk squared to by expanding the right-hand side. So this is wk minus 1 squared plus the feature difference squared plus 2 times feature difference and weight vector, right? So a plus b squared, or a minus b squared, is a squared plus b squared minus 2ab. Yeah? Then what we do is we make this assumption from the step before that the difference of the feature vector is bounded by r. So we can say this whole term is less or equal times wk minus 1 squared plus r squared. And that term cancels out because we set it to 0. And what we have in the end is we have an upper bound and a lower bound, and we can combine them and solve for k and get exactly our result. But it's just a little bit algebraic manipulation, not at all difficult. We can just solve for k in this term above, and what we get is k is less or equal than r squared times gamma squared. So what we get is k was our counter of errors. So we only updated k if we made an error, a mistake during training. And what we say here, k is equal, is less or equal to r squared times gamma squared. So if we maximize gamma squared, then the error will be small. Okay. So this is the explanation of the perceptron from the 1950s invention of the perceptron algorithm as an algorithm that just runs after the mistakes. And the proof basically was done by Novikov in the 1960s. And later on, people reframed the perceptron algorithm as an algorithm that takes a particular model and an objective function and applies convex optimization to it. And that's the way I like to see the perceptron. And this is a way of looking at the perceptron as an algorithm that optimizes a particular objective. And the loss function for the perceptron is the loss function here. It's what we, in the binary case, call the perceptron loss. So what it says is we incur a loss if our prediction, which is the maximum y, that is not the gold standard label, receives a higher weight than the gold standard. So we want to have the highest weight to the gold standard example, not something else. So if this term is positive, now sorry, if this term maximum, yeah. So it's a bit confusing because what we had before in the perceptron algorithm was our algorithm said that we do an update like this, right? Plus, we go in the direction of the positive example and away from the negative example. Now we are doing a stochastic gradient descent, and we are doing an update in the negative direction of the gradient. So what we have here is if we look at the perceptron algorithm as a stochastic gradient descent algorithm, we have to take the negative of this one. So the update we are doing for this objective is the negative of the gradient, and the negative of the gradient is minus feature representation of the predicted example plus feature representation of the correct example. And this is exactly the gradient of this objective here. So it's just a way of rephrasing the perceptron algorithm as an algorithm that takes an objective function and takes its derivative and then does a negative step, as a step in the negative direction of this gradient. So one last word to the perceptron. If you apply the perceptron algorithm, you probably don't want to apply the perceptron algorithm as it was invented initially by just doing one step after the other and taking as prediction vector the last vector. A better way is averaging all the weight vectors that you have encountered during your training. This is called the average perceptron. And we will see later on that this is a really good idea because you can give a proof that this is a good idea, that this generalizes better to unseen data. So to summarize what the perceptron algorithm does, it's an online learning algorithm. It looks at one example at a time and does an update, one example after the other, by following the negative direction of the stochastic gradient. Stochastic means the gradient for this one sampled example. And the intuition, and this is how the perceptron algorithm was invented, is that you go in the direction of the positive example and away from the direction of the wrongly predicted example. And we will learn more about online learning and stochastic gradient descent after the break. Thanks. So how long is the break?
Yeah, so it's here, the break.
How long?
How long? 15 minutes?
15.
Yeah. No.
Okay, let's get started again. So what we talked about before, we will extend this now. The next section is called support vector machines. It's an extension of the perceptron algorithm. And the idea of support vector machines is to optimize the margin directly. So what this perceptron does is it optimizes the margin implicitly. The margin means, for binary classification, the distance between the separating hyperplane and the positive and negative examples closest to the hyperplane. So the idea of the margin is if you have a large margin on your training data, then you will do good on unseen data because you have a lot of wiggle room to adjust your prediction on unseen data. If you have a very small margin, then it means that you have been running after the examples in your training set too closely. So let's the examples that we have here tell us. So you can see this margin here is very small, right? So it's very close to the negative and the positive example. If we would put it like this, then it would be larger and do a better separation. So if we put the machine that has a larger margin on unseen data, we are running less risk of overfitting to our training data. So the support vector machine is maximizing that term that we have been using in the perceptron proof directly. So it's maximizing the distance in classification of the gold standard example over all the other examples explicitly. And why would that be a good idea? To remind you, what we had in the perceptron convergence theorem that applies to any machine learning algorithm, namely that the error on unseen test data, so that can be shown explicitly by a cross-validation scenario. So cross-validation means you train, let's say, on 1/10 of your data and test on the last bit. Then you train on partition 2 to 9 and test on the first, and then you train on 3 to the end and 1, and so on. And you do this, you average the error that you find on your unseen holdout part, so by the number of splits that you do, and then you can say the error on unseen test data is proportional to r squared divided by gamma squared times t. So minimizing the error is done by maximizing the margin. So if you could maximize the margin explicitly, you would have a better way of generalizing on unseen test data. So in difference to the models we saw in the very beginning, like naive Bayes and logistic regression, that only looked at applying techniques for convex optimization to a particular training set where you optimize the likelihood on the training set or minimize the negative likelihood on the training set. This now changed a little bit by optimizing a criterion in addition to the error on the training data that tells you about unseen data. And this falls out of the proof that we gave for the perceptron. Maximizing the margin is a good idea if you want to have a good result on unseen data. So this is how machine learning comes into play in the application of convex optimization. It's something new and different now. Okay. So let's set up this problem explicitly as an optimization problem. Let's say gamma denotes our margin. We want to maximize the margin subject to the constraint that the weight vector equals, so then the norm of the weight vector equals 1, the same argument as before. You want to have this constraint in order to avoid these trivial solutions of just scaling the weight vector. So what we want is this term here, the weight vector, assigns a higher score to the gold standard example than to all the other examples by a margin gamma that is greater to 0. And this is again explicitly this constraint why we want to have the norm to be 1. If we set this up, this maximum margin problem, and do a little bit of reparametrization, then what we get in the end is the formalization that you normally find in textbooks for the support vector machine problem. And this optimization problem for support vector machines, it's not really intuitive why this has something to do with margin maximization and error minimization, but I will show you how from this very simple objective, maximize the margin, you get to the support vector machine problem. So what we do is we just, instead of using our weight vector W, we use another reparametrized weight vector, namely we use a weight vector U, which is just a scaled version of W. So if we use the constraint that the norm of W is 1, then we see that the norm of W is 1 if and only if the norm of U is 1 over gamma. Or in other words, gamma is 1 over the norm of U. So what we do is we use this reparametrized form and plug it into our objective here, and then with a little bit of calculations we get another form that is the form that you standardly see in the textbook, and by following this calculations you understand why you have this funny form. Because, yeah. So the first step is, instead of maximizing gamma, we maximize U 1 over norm of U, yeah? Because gamma is 1 over norm of U. So maximizing the inverse is the same as minimizing the term itself. Then we replace W here by U times gamma. And then you can see that the gamma cancels out. And this is one of the interesting things. People, when they see this form, which is the standard form, the first time they ask, why does it have to be 1? Why does the margin have to be 1? Well, it just falls out of this reparameterization. It's what we are doing here is we have to have a constraint in order to avoid trivial solutions, and the constraint here was the norm of the weight vector has to be 1, and now the constraint is the margin has to be 1, right? So it's as trivial as that. It's the same constraint. It's not something like 1 is a better number than 2 or 3 or 1/2. Yeah, it's just it falls out of this way of setting up the problem. Okay. So this is the standard form of the support vector machine problem that you normally see. You minimize some weight vector, namely the squared norm of half of the weight vector, subject to the constraint that the margin is greater than 1. And the margin being greater than 1, as I just said, falls out of this reparameterization. So it's exactly the same problem. What you do here is exactly this. Maximizing the margin means minimizing half of the squared norm. And this is your margin constraint. So this is a constraint optimization problem. And in the early textbooks, this constraint optimization problem was actually solved by constraint optimization solvers. There were different algorithms that applied off-the-shelf constraint optimization solvers to this problem, or other special purpose constraint optimization solvers. What we do nowadays, we apply our beloved stochastic gradient descent techniques to the support vector machine problem. What we have to do is we have to reformalize this constraint optimization problem as an unconstrained optimization problem. Then we can do stochastic gradient descent. I'll show you quickly how this is done. Just to explain why those things are called support vector machines. Because what you see here, what's the vector, what's the support? The idea of the support vectors is, by vectors you mean the feature representations or the input data. This is the vector, and the support vectors are the examples where the margin is exactly 1. So those are the examples that are exactly at closest to your separating hyperplanes, and they are called support vectors because you can basically say that the entire optimization problem only rests or is supported by the data that are closest to the hyperplane. You can ignore all the other training examples. And this is one way of looking at generalization of support vector machines by saying, these machines are really good because they can represent our training data by a few supporting examples. All the other examples are not important. We can leave them out. And the fewer of support vectors you have, the better you do in generalizing, because you find prototypical examples for your training data that you can apply to test data. That's one view of looking at support vector machine. Another view is we can look at this term here, which is the term, as we just saw, that expresses maximization of the margin. Yeah, doesn't look like it, but that's what it is, right? Minimization of this norm of the weight vector, as we just saw, is the same as maximization of the margin. We can look at this term as a regularization term. We will talk about this also. And then we can say regularization is another way of explaining why some learning algorithms do well on unseen data, because regularization means you have some constraints on your learned weights which make sure that you don't overfit on your training data. You make sure that the weights that you learn are good enough to get a good result on the training data, but they are not too closely tied to the training data. They are not running after every single example. The weights can't be too large and too small. Because if they are too large and too small, it means there must be some outlier somewhere, and in order to capture this outlier, in order to move the hyperplane, so in order to classify this outlier correctly, you have to set a very, very high weight for some feature, or a very, very low weight to some feature. So this is not good. Okay. So this is just on the side. Why are those machines called support vector machines? Because that was once upon a time the way of explaining the generalization power of support vector machines by looking at examples that support the hyperplane. And in order to derive the algorithms to optimize the support vector machine objective, we do some modifications. The first modification that we do is we make the model a little bit more expressive than the perceptual algorithm by taking care of the problem that the data might not be separable. So for the perceptron, we always assume that the data are separable by a margin of gamma. This is mostly not true. So what do? What we say is, in addition to margin maximization, we have a term xi, and the xi term is a slack variable. So what we say is the margin has to be greater than 1 minus xi. So we can make an error in our margin. So the xi, the larger xi, the more error we allow, right? So we can overshoot and undershoot in our margin. So, and we add this term into our objective. So if we have a minimization here, then what we have to trade off, we have to minimize this term, so we have to maximize the margin, and on the other hand, we have to make sure that this error term is as small as possible. So basically what we have is we have an objective that consists of two parts, namely an error term or a loss term and a margin term. So, so this C, this scalar C parameter, this meta parameter, this balances the focus on margin and on error. So which ranges of C focus on margin and which ranges focus on error? So how do we have to set this parameter if we know that our training data are linearly separable? So we can really focus on minimizing the error. We don't, margin maximization, not that important. How do we do that? By setting C to what? 0? 0 would be good, yeah. No, if we want to make sure that this term is taken very importantly, we have to set it to 1/2 or more, right? If we set it to less than 1/2, we are focusing on the margin, right? 1/2 is the splitting point. Greater than 1/2, then this will be very important, right? Let's say C is 1 million. Then in order to minimize this term, we have to put all of our focus in minimizing this term here, right? If it's a very small value, then we can ignore it and just focus on the margin, right? This is one of the important hyperparameters for support vector machines. If you use tools for support vector machines, and you have to know what the properties of your training data are. Do you really have to focus on margin or on error? Yeah?
Can you explain how C depends on the number of training systems? So here is no normalization over the number of training systems. Here that many training samples means that if you already focus more on one vector.
Yeah. I've never thought about that, I have to admit. I guess if you have a lot of training examples, then you don't have to focus on margin maximization that much, because you have basically overfitting on the training data, if it's really, really large, is not that big a problem because you won't be able to do it anyway. Yeah?
We don't need to set C depending on the number of trainings?
That would be maybe one idea. If you know that you have a very small training set and it's maybe noisy as well, then you have to focus on the margin more than on the error. Because focusing on an error on a very small training set that you don't know very much about is not a good idea. Yeah, that's a good point. Yeah. Okay. So now that we have introduced the slack variables, we still have a constraint optimization problem. That can be, now it's a quadratic optimization problem, and there are toolkits for quadratic optimization that can be applied readily to this task. But what we want to do is we want to reformalize this objective so that we can apply unconstrained optimization. So what we had here is, again, a constrained optimization problem. So how do we do this? So the idea is that we want to fold the margin term into the objective by expressing our error term in terms of the margin. So what we had before, right? So we had this expression. The margin has to be greater than 1 minus xi. So we can express this here in terms of xi. So we can say xi is greater than 1 plus the negated margin, maximum score for the prediction minus score for the gold standard. Then we can plug this in here. After not using the C parameter but the lambda parameter, this will be useful in order to understand what we have here as a problem where you, on the one hand, you have an error term or a loss term, and on the other hand, you have a regularization term, and the regularization term is normally the one where you put this hyperparameter on. So you basically say, how much do I want to regularize my objective? And then what we had before here, xi is greater than 1 plus this term here is put into our objective by making clear to us that xi is either 1 plus the maximum score for the prediction, also the score for the maximum for the prediction, which is the maximum label, minus the score for the gold standard, or it's 0. It's 0 if we don't make an error, and it's this term if we make an error. So what we can say is our objective basically is what we have down here. So the xi is just replaced by this term here. So our loss function, our unconstrained optimization loss, is now the minimum of a loss plus a regularization term, where the loss, it's called the hinge loss, is exactly how we replaced the xi term, namely the maximum of 0 and this term here. So 0 is when we don't make an error, and this term here is when we make an error, and error for the support vector machine means that the score that we assign to our prediction is greater than the score that we assign to the gold standard by a margin of 1. Yeah, if this means we make an error by assigning a higher weight to the prediction than to the gold standard. And this assigning a higher weight, it has to be, if we don't want to make an error, this assigning of the the gold standard, a score has to be higher than assigning a score to to the prediction has to be more than a margin of 1. Otherwise, we make an error. So this is our error term. We incur, for every example where we make an error, we incur this term. And then we have, on the other hand, we have this regularization. So this is an unconstrained optimization problem that we can take the derivative of and do stochastic gradient descent. And I will show you later that this is, if you do stochastic gradient descent for this objective, it's very similar to doing stochastic gradient descent for the perceptron algorithm. The only difference is we have a slight difference in our objective, and we have this additional regularization term. And for the support vector machine, the nice thing is this regularization term can be explained as margin maximization, as I explained to you before, right? So it doesn't fall from the sky, so it has a clear interpretation. Minimizing the norm of the weight vector is the same as maximizing the margin. And this is our error term. Okay. So now what we have covered is we have looked at 4 different objectives that are formalized for 4 different linear models. The naive Bayes model that made this independency assumption, the logistic regression model that didn't make the independency assumption, but instead used this normalization constant. Then the perceptron and the support vector machine, where the perceptron and support vector machine, they didn't really maximize the likelihood, but they optimized some error term, right? So the error was you have to predict, you have to assign a higher score to a gold standard example than to your argmax example. And the support vector machine differed from the perceptron by optimizing this margin term explicitly. But all of those techniques were the algorithms that we had seen so far, naive Bayes, logistic regression, perceptron, they could all be derived as applying constrained optimization or unconstrained optimization to an objective. That always was based on training data, right? The likelihood of the training data or the error on the training data. And now what we will see in the next 3 sections is general techniques from machine learning that go away from the objectives of constrained optimization, which is just optimize your objective function, minimize your negative log likelihood or something like that, to do as good as possible on unseen data by applying regularization. Then other techniques like online learning make sure that the algorithms are as efficient as possible. And then in the last section, how can we infuse non-linearity in our simple linear models without giving up all this nice machinery of convex optimization that we used so far. Okay, so regularization. What is this all about? So let's look at 3 very simple logistic or regression problems. This is the data points we have. And what we do is, here we have a linear model, here we have a polynomial of order 2, and here a higher order polynomial. And each of those functions, they are more expressive from left to right. And more expressivity means that we can fit our data points better. But as we will see, there's a trade-off between high variance, which means we are fitting the training data too closely, so we are overfitting on the training data because we can't be sure that our test data, that the next point will be really, yeah, I don't know, maybe it's here, right, the next training data, the test data point, and here, and we do something wrong. So maybe, and this is not close enough, so we have to find something, we have to trade off bias and variance. So variance is the variance that depends on the training data, and the bias is what the model tells us about how the classification should look like. So how powerful should the model be? So another example to show you that it's not enough to fit the training data perfectly is this one. So we have two curves, the dotted one and the solid one, and we have 3 training data points for binary classification: negative example, positive example, negative example. And we see both of them perfectly fit the training data. Yeah, they make the right prediction for the positive and negative examples. But for all examples that lie in between, they make different predictions. And this is, in general, you can always find, for any given function, you can find another function that fits the training data just in the same way as your function, but does something else, something different on the test data. So fitting the training data is not enough. You have to have some handle that tells you, how can I not just fit the training data, but make sure that I don't overfit on the training data? How can I make sure that on unseen data I'm doing the right thing? And the idea is we have to think about capacity. Capacity means the model has to be just right, powerful enough to model the training data, but not too powerful. Okay, so the idea of making sure that you find the right trade-off between fitting the training data and taking care of unseen data is what I will call here regularization. And we can basically, what we have seen before, we can reinterpret what we have seen before in those terms. So basically, if we look at the maximization problem, we have a loss function or a maximum likelihood objective, a likelihood function that we want to maximize, and we have a regularization term. So if we maximize this joint objective, then we have to make sure that we fit the training data as good as possible, but we also have to make sure that, let's say this lambda is a very high value, that the regularization doesn't incur too much penalty on our objective, right? So we have to make sure, depending on what this regularization looks like, that this term doesn't grow too large. Otherwise, our maximization would be, this would counteract. So, and the standard way of setting up a regularization term, or a very simple way, is to take the squared norm or the 2 norm of the weight vector. So what the effect of this is, smaller weights are desired. So what we are doing is we are making sure that in our optimization, if some weights have very high values, positive or negative, this is not good, because then the norm of the weight vector will grow large and the overall objective will not be maximized as good as we could if we would use other weights meaning smaller weights. And why is this a good idea? Because you can be sure if you have some outrageous high or very low weights that you are running after some outlier examples. You can basically, if you look in the log file of your training routine, and if you do online learning, then you can look for each example, which example is responsible for all of a sudden janking up one weight to a very high or very low value. And this will be an example that is not representative for your training data. And you don't want to adjust your parameters to fit this one example. Most of the time you can find something like that. Okay, so that's the idea. So, and the idea is so general that we can apply it to any of the algorithms that we have seen so far. So for example, for the logistic regression objective, where we had a maximum likelihood term here, we can just apply minus lambda half times the squared norm of the weight vector. And that way we make sure that the logistic regression objective, which on its own just maximizes the log likelihood of the training data, has something that prevents overfitting by adding or subtracting this term here. So all we have to do in the gradient ascent or a gradient descent, we have to take the derivative of this new term, which is very simple. The derivative of lambda half times the squared norm is lambda times the weight after which for which we took the derivative. So in your algorithm, you will just have the gradient that you had before, and for each component you will have minus lambda times wi. So intuitively, if you just look at the algorithm, what this does is you are doing an optimization, and at each step of the optimization, you are pulling back your gradient-based step by lambda times minus wi. So you're making sure that you can't overfit on the training data. If you set this lambda to a high value, then you're going in the direction of the gradient, and you're taking one step forward and half a step backward. Yeah. And for support vector machines, yeah. So that's exactly the difference of the perceptron to the support vector machine. The perceptron is very much an algorithm that does not include a regularization term. So it's a very simple, stupid algorithm. It doesn't take care of maximizing the margin or regularizing explicitly. So the perceptron is very prone to overfitting the training data, because it doesn't include this regularization term. So I started with logistic regression. Then we look at the support vector machine, and the nice thing in the support vector machine is that the L2 regularization that we used before, this is just the loss function, the hinge loss function for the support vector machine. The L2 regularization can be interpreted as margin maximization. So we have an interpretation of this regularization term that goes beyond this simple intuition of what we are doing is just making sure that the weights can't grow too large or too small. What we do is, in the support vector machine, we are maximizing the margin. And we showed this by the derivation of margin maximization, and where we ended up with exactly this L2 norm. Yeah? This was how we formalized the margin maximization. And now it makes sense from two ways. It's margin maximization and minimizing the norm of the weight vector. But this L2 norm is so general that you can apply to any loss function. This is the SVM loss, and this is the logistic regression loss. Okay, I'm not talking about the perceptron here because I will talk about it later. Again, the perceptron doesn't include this term here, right? The perceptron loss was just, it had a loss like this, no regularization term. Okay, but what I want to tell you now to finish is this section on regularization. Why does regularization make sense? How can you prove that regularization makes sense? So as we showed before, this is again the same. It's based on this convergence bound for the perceptron algorithm that we have seen before, now just generalized by cross-validation to unseen data. That the term, the gamma squared term here, we initially interpreted this as a margin, right? Margin maximization makes sure that the error on unseen test data is small, And if we interpret the margin maximization as minimization of the squared norm of the weight vector as a regularizer, then we can use the very same theorem that tells us margin maximization is a good idea, and say L2 norm minimization is a good idea. L2 norm minimization makes sure that the error on unseen data is smaller, yeah? Because we can interpret margin maximization as L2 norm minimization. So we can reuse this theorem, this simple theorem we saw before, in order to explain how this lambda divided by 2 times the norm of the weight squared, if we add this simple term to our algorithm, we will do better on unseen test data. And another proof, that's an older proof that interprets this whole business, this regularization business in terms of support vectors. That tells us that the error on unseen data is smaller, the smaller the number of support vectors is. And the intuition behind this is, if you are able to support your decision boundary by a few examples, then you will do better on unseen test data. So basically, if you can find a separating hyperplane that takes out of 1 million example only 500 and spans this hyperplane, supports the hyperplane by these examples, then, and you don't basically use the other examples, then this will give you power for unseen test data, because you didn't adjust all the weights already, so you have something that is more flexible. But this can be shown formally, right? So I'm not just giving intuitions. All of those things, you can look it up in the Wapnick book, and you can look up this proof in Froy and Shapiro. So I'll have a little list of references in the end. Okay, so now we can summarize. We saw this plot before. When we talked about objective functions, now you understand better what I mean. So this loss here, this is the perceptron loss. The perceptron loss didn't take care of a margin, right? So it only makes a difference between correctly classified example with 0 loss and incorrectly classified example with a linear loss. In difference to the support vector machine that has also a hinge loss, but it has a margin of 1, right? So we want to make sure that we classify correctly, and we even penalize examples that are classified correctly but not correctly enough, so to say, right? So they have to be classified at a margin of safety of 1, right? We have to make sure that the positive example gets a score that is higher than the score for all the other examples by a certain margin. And the red curve is the log loss. That exactly corresponds to the logistic regression loss. So all the algorithms that we saw before, they are based on different kinds of losses that are upper bounds to this 0-1 loss. They're convex upper bounds. So from a convex optimization perspective, all we are doing is we are setting up convex functions and we are doing minimization. From a machine learning perspective, we are infusing these convex optimization algorithms by different ideas that make sure that we do well on unseen data, like margin maximization. Or penalizing errors exponentially instead of linearly. Ideas like that. Okay, now let's go to making sure that the algorithms that we're using are efficient enough to be used on large data. So this is what online learning is about. So online learning basically has already been implemented in the perceptron algorithm. So if we look here and remember what the perceptron algorithm looked like, so what we did for the perceptron algorithm, we ran through our training data, and for each training data, what we did an update. So we checked if we can correctly classify this training data, and if not, then we did an update. So we pushed the weight vector in a certain direction. And in difference to online learning, batch learning is what has been was the initial way of doing machine learning or convex optimization, because the objective you're looking at is always an objective over the whole training set, over the sum of losses over the whole training set. So what you do is you run over your whole training set and you calculate the gradient for the whole training set, and then you do one update. So batch learning means you look at your training data as one batch and do an update for the whole batch. Online learning, the extreme case is you do it example by example. Then there is something in the middle, which is mini batch, so you do updates for a small number of training examples at a time, right? But those are the two extremes. So what batch gradient descent does is it computes, as I said, for this loss function, which is the sum over the losses for the training examples, the gradient. So the sum over the gradients of the losses, if the losses are decomposable for training examples. And stochastic gradient descent does it per example. And the name stochastic comes from the initial idea that you're not having a training set where you run through the training set one example after the other, and they are ordered as they are given to you by some routine. But what you have is an infinite sequence of examples that are sampled, that are given to you by some random process, some stochastic process. You can emulate this scenario if you have a fixed training set by sampling training examples from this training set. You can do the sampling by sampling with replacement or sampling without replacement. So you have to make sure that you have some stochasticity in your sampling procedure. And then you can call your algorithm a stochastic gradient descent algorithm. So logistic regression, one way of doing optimization for logistic regression is applying this idea of stochastic gradient descent. So what we do is we calculate the gradient on a per example basis. So we calculate the gradient of our loss function, which we saw, it looks like this. On a per example basis, we sample one example after the other and do an update. We can apply the same idea to support vector machines, and this is, I would say, the best way of optimizing support vector machines. You are not applying some quadratic optimization techniques to the constraint optimization problem. What you're doing is you're formalizing this hinge loss objective, and you're taking a stochastic subgradient descent routine on the hinge loss objective. So the loss function means you're taking the gradient of your hinge loss. And the gradient of the hinge loss, it's 0 if you do the right prediction, meaning the score that you assign to the correct example is greater than the score for your prediction by a margin greater than 1. And otherwise, you are doing an update. And the update is you're going in the negative direction of the gradient, and the gradient of this term here is just the feature vector. So this is, if you are not using linear models here, then you would have to write here gradient of your objective, right? But it's the same idea. You can, so I had a question before, how would this apply to nonlinear models or to neural networks? It's very same idea. If you have a neural network where the model is a complex, layered, nonlinear function of feature, input feature representations, then what you have, you still have something like a gold standard example. You still have something like a prediction over different outputs. And what you have to do is you have to make sure that the gradient for your score, your nonlinear score for the gold standard example, is larger than, or the score that you assign to your gold standard example is larger than the score that you assign to any other example by a margin than 1. And what you then do in your update is you just take the difference between the gradient for the gold standard example and the gradient for the other example. And the gradient has to be computed by backpropagation. And here, for the linear model, it's very simple. The gradient is just the feature vector. So there's nothing special in this. It's just, it's very simple to understand because the gradient it's done in one step, right? The gradient of a linear function is just the feature representation. But it can be applied to any other more complex model as well. And that's what is done, actually. I mean, if you do most of the neural networks, they are optimized by stochastic gradient descent in the same way as we optimize logistic regression, support vector machines, and now this is the connection perceptron and support vector machine. As we heard before, the perceptron is stochastic gradient descent optimization for a hinge loss objective without margin. Yeah? This is the hinge loss objective for the support vector machine, where we have this lambda times w that comes from the regularization or from the margin maximization, and we are just missing that in the perceptron. The perceptron is so very much an online learning algorithm like the online support vector machine. It just doesn't do any explicit margin maximization or regularization. So that's why the SVM is a better learning machine than the perceptron. And nowadays in neural networks, when you stack perceptrons onto each other into multi-layer perceptrons with recursion or without and so on, what you always see in the end, what people use is they use some regularization, L2 regularization. So they actually, what they are stacking onto each other is not perceptrons, but support vector machines. As soon as you use this regularization, you can interpret what you're doing as you're actually implicitly maximizing a margin. Okay. So to summarize differences between online and batch learning, so from a convex optimization perspective, batch algorithms are actually to be preferred because they converge faster. Yeah? So this is always what's important for convex optimization. Both algorithms will converge eventually, but faster convergence is better. And why do they converge faster? Because the gradient steps that you're doing, when you average over the whole data set, over the whole training set, it's more stable. So each update has more information and more robust information. Whereas when you do online learning, the computational cost is less, but each gradient step depends on one example. So what you're doing is you're basically, for every example, you are changing your the weight vector that you have learned on all the examples before. And the examples might be outliers, they might not be representative, so you have to be very careful in order to make too large steps on a per example basis. So the reason why online algorithms convert slower is you have to make sure that the learning rate is small and decaying. So you only can show convergence for online learning algorithms if you make sure that the learning rate is getting smaller and smaller and smaller. Otherwise, the error will always be there. The error that is introduced by stochastic choice of examples. For batch algorithms, you can show theoretically with a constant learning rate, even a large constant learning rate, you will converge. But that's just theory. So what people do is they use stochastic online learning algorithm with large constant learning rates, and it still works. Okay, but question, so what would you do in big data scenarios? Would you do batch learning because of faster convergence, or would you rather do online learning? Why? I guess the most important point is this here, right? If you have really, really large data sets, then if you have to wait until you have run through the whole data set once in order to do an update, you have to store this update somewhere in memory, and so it's just not feasible. It's from a computational perspective. If you could get around these computational problems, maybe it's doable. I mean, companies like Google, who have lots of machines and can parallelize very easily, they do what they call mini-batch training, but the mini-batch sizes are, nowadays, they have a size that the training sets that we used in machine translations had 10 years ago. So each mini-batch is now the size of a large training set from 10 years ago. So if you have the computational power, then you will want to have a trade-off between stochasticity and batch learning, so large mini-batches. And you also want to do, never mind. Yeah? Yeah? So there are a lot of papers on batch sizes. So there's one paper by Keskar et al. So where they show that if the batch size is too large, the problem that you're running into is you are learning very sharp minima. And what you want to learn is, so for non-convex optimization, what you want to learn is you want to learn very flat minima, because the flat minima generalize better on unseen training data. And they showed that on particular machine learning problems. Then a month later, another paper came about that showed no, even large batch sizes, they don't have the problem. You can tune them to in order to fit this peaked minima, and so it's an open problem. It depends on applications. Most of the papers that have been done on talking about generalization for neural networks are experimental. They hold for the data set and the architectures that you show them for, but they don't hold in general. I don't know very many principled papers that show this is true for all kinds of architectures, for all kinds of applications. So, I'm sure they are right. For this data set, it might be true, but for another data set, things are again totally different. Yeah. Well, you have to tell me which paper proves for all times for LSTMs that, yeah. Okay, let's continue. So what I want to show you is one of the things that you will hear about later on very frequently is something like variance reduction in online learning. This is a very important point, because if you make sure that you have some technique of reducing the variance that is introduced by the stochastic choice of examples, then you can make online learning as good as batch learning, so converging as fast as batch learning without losing all these nice properties of being easier to implement, doing more updates while you run through your training set. And the idea, so one of the simplest ideas already invented in the 1960s is to use a momentum term, and momentum means if this here is what we had before, this is just stochastic gradient descent, we go in the negative direction of our gradient. What we do is we add a velocity term, and the velocity term is just the difference of the weight vectors from the step that we look at the moment and the step before. And if the two weight vectors, if the weight vectors that we're looking at in our update at the moment differs from the weight vector that we had before, so if they are orthogonal, then what we do is we are adding a term to our optimization problem. So we are basically making sure that whatever we are doing when we follow the negative direction of the gradient is taken back, because we don't want to go in a direction of a gradient that is orthogonal to the gradient that we have established before. And if the gradient direction is roughly similar to the direction that we have seen before, then this term cancels and we can do a large gradient step. So basically what momentum does, it smoothes the optimization surface. So we can really follow the valleys, the ground of the valley where the gradients are aligned. So we're not going up and down the hill. It's very simple by doing this velocity. And this is what is built in all of the techniques that you use that are called eta grad, Adam, eta delta. They all have some way of doing momentum. And well, basically there are three different techniques that the new stochastic gradient descent techniques do. One is momentum, the other one is they have a learning rate that is adjusted per parameter. So not one constant learning rate for all parameters like we have here. And yeah, basically those two. And they're done in different ways. And they have a decreasing learning rate. Yeah, okay, so you have a learning rate that is done per parameter, and it's decreasing depending on how important that parameter is. So it's decreasing and increasing. So it's per parameter, decreasing, increasing, and you have something like momentum. So across time, you're also making adjustments. But all the algorithms that you're using nowadays, they are all based on this simple stochastic gradient descent idea with momentum. Okay. So one of the things that you have to take care of when you do natural language processing is online to batch conversion. So all these online algorithms, they basically have been invented for the scenario where you have an infinite sequence of training data coming in, and what you're doing is for each new training data you make a prediction and you do an update, and then you go to the next examples. So ideas of where this applies in real life is online advertising, where you can where you see new users looking at ads, or personalization for web pages. So the new web pages pop up, new users come in. But for the standard NLP applications, where you have finite training sets and finite test sets, and you loop over these finite training sets and test sets, and what you have to do in order to write a paper is to show that on a fixed test set, you get an improvement of XX points. You have to make sure that your online algorithm can be applied at test time in a batch fashion. So you have to basically make a choice of which parameter that you learned while you're doing online learning has to be used for testing. So is it the last model, like in the standard way of using online learning? Do you randomly choose one of the weight vectors, or do you choose a model on a held out set? So by doing an evaluation on a held out set, so this is not supported by the theory, right? So the theory that we showed for the perceptual algorithm didn't say anything about held out sets, right? It just told us we are converging on the training set to an error that is bounded by some terms. So what do you do? One idea is using averaging, like we saw it in the average perceptron. It doesn't always help, but at least there's a theory that tells you if you use the average weight vector that you find by just averaging all the weight vectors from step 1 to step t, then you can show that the expected error on unseen training data is bounded by the error that you made during online learning plus this term here. So this term is decreasing in k, so the more training data you see, the smaller is the error, and this is a confidence parameter, 1 minus delta. So you basically, what you can say is, if you do averaging, then you can give a proof. So you can read it up in this paper by Cesar Bianchi. The error that you make while online learning is an indicator of the error that you will make on unseen test data. The expected error, it is bounded by the error that you make during online learning. And this is a very useful technique to find out how good your model is, how good your parameters are, by checking the errors that you are making during online learning before you apply it to your test data. And this can be applied to all convex losses, so it doesn't apply to non-convex losses. But yeah. All right. So we're nearly done. Again, we saw 4 different models or algorithms based on models and objectives. Then we learned about gradient descent, convex optimization. We learned about regularization, which is not core convex optimization. This is core machine learning. And then we learned about online and batch learning, which is also, yeah, it's in between machine learning and convex optimization, because some of the proofs in the convex optimization literature, they just care about what converges faster on the training set, and then there are some papers that show that the stochasticity that you have in online learning actually is helpful to prevent overfitting on unseen data. So this is always a trade-off. If you have to find the right way of randomization. Randomization is good and bad. So it's bad since it takes a long time to converge, but it's good because you are making sure that you can't really overfit on your training data, because there is something random going on that you don't have in your hands. It's always a bad idea to just mirror the training data. Yeah. So the last section I will talk about is how can we basically pimp our linear models? How can we make the linear models be more powerful without losing all the niceties of convex optimization? So the niceties, I mean, there's the guarantees that we find a single global minimum by doing our stochastic gradient descent steps. So the idea is most of our training sets are not really linear separable. They look like in 2 dimensions like this. So this is not a linear decision boundary. We have to make sure that we can find a classifier that finds a decision boundary that looks like this. How do we do this? So one way is, it's called kernel machines. So the idea is to take the feature representation and project the feature representation into a higher dimensional space, but make sure that this projection into higher dimensional space does not affect the learning. So it's only, we have to know how to do the projection. So it's a fixed way of doing, infusing nonlinearity into our model. But we are not learning parameters for this nonlinearity. So that's the trick of keeping, how we can keep the convex optimization guarantees while still having the ability to doing nonlinear decision boundaries. by just making sure that our feature vectors are now represented in higher dimensional space. So, and the origin of these ideas, they were done at the times when support vector machines were the state of the art in machine learnings. And support vector machines, they can be formalized as algorithms that are based on dot products of feature representations. And kernels are similarity functions. So the machines are called kernel machines because what they do is they take this dot product that is part of the algorithms and make sure that by modifying the dot product, you get a higher dimensional feature representation. You can pimp the algorithm by basically tuning the dot product, by making the dot product more expressive. So one of these ideas is, let's assume we have an algorithm, and we will show how we can do that for the perceptron, that is based on dot products, on similarity functions. So what we want to do is, we want to show how this making the dot product more expressive corresponds to making the feature vector implicitly more expressive. But let's start with the feature vector. So one of those, also one of the well-known feature representations that make sure that you can do nonlinear classification is the monomial feature vector. So it's basically just an ordered and disordered product of the entries of your feature vector. So for example, a fourth order product of it, if we do a mapping from 2 dimensions into 4 dimensions, and the fourth order product of 2 feature components would be, we multiply each component with all the others. So x1 squared, x2 squared, x1 times x2, x2 times x1, right? So we now go from 2-dimensional space into 4-dimensional space. And this simple feature representation, this monomial feature representation, it introduces a nonlinearity that allows you to solve machine learning problems that are not linearly separable. So one example, which I won't give, but it's a standard example that motivates multi-layer perceptrons. So this XOR problem, this can be done exactly by monomial features. So you can, the XOR problem, the exclusive OR problem is a nonlinear problem, and you can solve it by using this nonlinear feature map. Why is it nonlinear? Because you have these products here, right? So how do we compute a kernel from this feature map? Let's say our learning algorithm includes dot products of examples, phi of x, dot product phi of x prime. So the dot product is just the sum of the product of the entries. What we do is we expand the feature representation from 2 dimensions to 4. So we have a sum of the feature representations and products x1 squared, x1 prime squared, x2 squared, x2 prime squared, and so on. And we can see that this can be simplified to x1 times x1 prime plus x2 times x2 prime squared. So basically, what I want to show here is it's easier to directly modify the kernel, so directly modify the dot product by just taking the dot product squared instead of first expanding the feature vectors and then computing the dot product, right? This involves more computation than this here. You just do the dot product and take the square of the result instead of unfolding the feature vector and then computing the dot product. And this example is instructive because what I want to show on the next slides is there's a general theorem that tells you for every kind of kernel, or kernel is just a dot product, for every kind of dot product where you do something to the dot product, like you square it or you do something else to it, there is an implicit feature representation, and the implicit feature representation is more powerful than your original feature representation. And the idea is, if you modify the kernel, then you can be sure that what you do implicitly is you are pimping your feature representation. You're making your model more powerful by implicitly using a more powerful feature representation. And the kernel will give you the power of doing nonlinear classification, which you couldn't do before. So this is the general theorem. It says for the monomial features, if you have a kernel that is a disorder product of your kernel, then for each monomial feature map that is the disorder product of monomial features, you can get a kernel like this. So an example why for two different kernels that give the same feature representation is before we had we mapped R2 to R4, right, by this representation here. We took basically an ordered monomial feature map. Ordered means there was a difference between x1 times x2 and x2 times x1. Now we take an unordered monomial which has dimension 3, but it has the same effect. The kernel is the same. It's the dot product of the original feature representation squared. Because if you plug this into this derivation, you will end up with the same result, right? Taking this feature representation, unordered or ordered monomial will represent the same kernel. So, and the idea is you go the other way around. You say, okay, I have a kernel, and this kernel can represent a higher order feature representation. I don't know which one exactly. It could be the unordered or the ordered, but there is one. Okay, so maybe a question for those who know about image processing. Why would these monomial features or the kernels that are called polynomial kernels, why would they make sense? For example, for image classification. Let's say we're doing handwritten digit recognition, and we want to differentiate an 8 from a 0. How would the monomial features be useful? So what's the intuition behind taking a product of features? Yeah, let's say we have a feature that says circle. So if we don't have the monomial feature map, then we can't really distinguish the 8 and the 0, right? We have in the 8 we have circle, in the 0 we have circle. But we don't have a feature that says we have two circles. And the monomial feature does exactly that. It says circle and circle. So it says we have to have two circles present, so we can distinguish 8 from 0 by the monomial feature. That's one of the intuitions. Another intuition, so if we look at the two-dimensional example, so this is, for example, what you would get for the XOR problem. Just look at it as a nonlinear decision boundary. There is no hyperplane, no line that you can find that distinguishes the crosses from the circles here, right? In two-dimensional, hyperplane is a line. No way to do it. What do? We use our simple monomial feature map and map from 2 dimensions to 3 dimensions. So x1 squared, x2 squared, and square root of 2 times x1 times x2. And then we get this representation here. And you will see in this representation, we can differentiate the circles from the crosses by one of the circles lie behind this hyperplane, and the crosses lie on the right side of the hyperplane, right? So let's look at a few examples. So the small values which are in distance 1, 1, 1, minus 1, minus 1, 1, and so on, they will be mapped to something like 1, 1, and 1.4. And all other examples that are a little bit bigger than 1, they will be mapped to very large values, right? So you will basically push the examples that lie around this circle here to very large values and push them above the hyperplane, and the other ones are behind the hyperplane. This is done by this very simple feature map, which is not separable by a linear classifier. Okay. So this is the central theorem. If you have a kernel, so kernel meaning a similarity function that is symmetric and positive definite, then you can show that for any kernel there exists a feature map such that the kernel is the dot product of this feature map. So what we had before with this polynomial kernel and the monomial feature, so the polynomial kernel implicitly was the ds order dot product of the features, the monomial feature map, and we can now say every kernel that is positive, definite, and symmetric implicitly corresponds to some feature map. And most of the time it's a nonlinear feature map that allows you to do classification of non-linearly separable data that you couldn't do before. Okay, and this is the kernel trick is basically you find that in older textbooks. The trick basically is not modifying the feature representations explicitly, but just setting up kernels that are positive, definite, and symmetric, and not caring about the feature representation. If you have an algorithm that includes dot products, then you just make the dot product more expressive, and you can be sure implicitly what's going on is you are making sure your algorithm is more expressive. So let's do it for the perceptron. How can we kernelize the perceptron? So this is our standard perceptron algorithm, right? This is the update. Go in the direction of the gradient of the gold standard and away from the gradient from the prediction. And if we look at what's going on here, what we are doing is each time we are computing, each time we are incurring an error, we are adding this feature representation and subtracting this feature representation. And we're doing that alpha sub y t times. So yt means for all examples where we make an error for all instances of training data. So what we can do is we can basically say our weight vector is nothing else than a sum over t and y of this difference of feature vectors times alpha. Yeah? Alpha is the importance or is proportional to the number of times we made an error for a label y on example t during our training process. So if we use this representation of our weight vector, then we can reformalize our perceptron algorithm as an algorithm that uses a dot product. And when we have the dot product, then we just can replace the dot product by a more expressive kernel and basically can make the simple perceptron algorithm a classification algorithm that applies to nonlinear data and can separate nonlinear data. So the idea is this is our decision function, w times phi. We replace w by what we just said it is before, namely the sum over the feature representations for all the errors that we made, and then we take the dot product with our gold standard, with the example. So what we want to do here is we want to look at all examples and we want to find the examples that maximizes the linear score. So what we are doing is we have to compare all examples with the gold standard example and with the prediction. And what this is comparing is we are computing similarities, we are computing kernels. So what we are doing is we are, in order to find the argmax, we are doing a kernel similarity comparison of all the examples with the gold standard and of all the examples with the predictions. So we do that at training and test time. At training time, we replace our weight vector by this new term, and at test time, we replace it by this new term. And the intuition is, so y star, so the label that we want to find is the label that is most similar in terms of our kernel similarity to the gold standard, and it's least similar to all the other examples. Yeah? A good example that we want to predict is one that is close to a gold standard and not close to all the other examples. So this is basically the dual representation of the perceptron algorithm. So the representation of the perceptron that does not look at a linear combination of features and weights, but the weights basically are just comparisons of examples with all other examples. So a weight is how close is an example to all the other examples, and how is it closer to the gold standard or is it closer to the examples that are not our gold standard. And what we can do here now, if we have represented our perceptron as a kernel machine, we can just, for this K representation, instead of taking the standard dot product, we can take dot product squared, dot product up to the power of 3, up to the power of 4, and so on. And what this will do is, implicitly, it will give us a monomial feature representation that is more powerful than the linear combination of features that we had in the beginning. And of course, there is a danger of doing this, because what you do when you use kernels, like polynomial kernels of very high order, you make your model so powerful that in the end, what you will see is all your training examples are support vectors. They are all lined up close to your decision boundary, and you have shot yourself in the foot again by making the model so expressive that you overfit on the training data. So you again have to find the right trade-off between making the model powerful enough but not too powerful. Yeah? So this is why, in my opinion, what's really so nice about neural networks is that they learn this combination and selection of features automatically, so you don't have to choose as a meta parameter what the combination of features is. I mean, this is one of the feature representations or representation learning that is done in neural networks is exactly this, combining features by products, right? Using this logical AND operator and say, seeing these features together is a good idea, and seeing those features not together is not a good idea, and setting this feature to 0 is useful. But if you use kernel machines, then you have to know you have to do meta parameter search in order to find the right kernel. For neural networks, it's done for you in a way. Yeah. All right, so the summary for kernel machines, it's a nice way if you have a good handle on your kernels to turn a linear model into a nonlinear model without giving up the machinery of convex optimization. The kernels are not learned. The kernels are, it's a routine, it's a program that is done for you. So you're not learning parameters that weight that say this monomial combination is more important than the other one. This product is more important than the other one. It's not like this. So the disadvantage of kernel machines obviously is they depend polynomial on the number of training examples. Yeah? Because what you have to do is you have to take the dot product of all training examples with all training examples. And if you have millions of training examples, that's totally infeasible, right? So this is one big disadvantage of the standard way of kernel machines, but there's a solution to it. The solution is has been presented 10 years ago by Rahimi and Recht. So the example here is a recent application to speech recognition. And so this, the paper by Rahimi and Recht, so it got the best paper award at NIPS last year, or I think 2 years ago. So not best paper award, the proof of time award, right? A paper that has been cited and used very often over the last 10 years. And the idea that they had was instead of using kernels to make linear models nonlinear, let's go to the feature representation and let's do the feature make the feature representation explicit by randomization. So let's make the expressivity by inducing randomization in the feature map. So the randomization, so it would be, for example, you have a representation by, let's say, Fourier transformation, where you have a representation of your signal according a spectrum, where you have, well, maybe a better idea is binning. So you have your features and you have certain bins, and you represent your features by a random choice of certain intervals. So this randomization that you randomly choose to represent your input data by only looking at certain bins. So which feature ranges are important to represent my input data? This introduces nonlinearity. It's a selection that is nonlinear in the input feature representation. And this randomization, of course, it's done, you always use the same random bin for the same input data, but this randomization introduces nonlinearity without any work at all. By just randomly representing your input data by certain bins or certain elements of the spectrum, if you have a Fourier, if you have a continuous feature, you can basically look at what you're doing as a very simple neural network where you have a random number representation of the input features that introduces nonlinearity, and then you learn linear weights from the hidden layer to the output layer. And you can do this by convex optimization. And these models, they work just as well as convolutional neural networks for speech recognition. So doesn't mean that they are any better or whatever, just saying there are other ways of introducing nonlinearity in your linear models that are not costly, that are even less costly than training a neural network, namely this work by Rahimi and Recht. You should look at it. It's, I have it on my on the references slides. Okay. So how much time do I still have? I'm over time already. Yeah. Okay. All right. So then 2 slides, and then I'm done. So summary, the basic. So what I wanted to teach you is basic principles of machine learning. What you do is you set up a model, you set up an objective function. For linear models, the objective will be convex. Then you use convex optimization. And if you are interested in nonlinear problems, you introduce nonlinearity by kernels. And you're done. The algorithms, they are just by using the very same routine that is used for modern machine learning problems, namely stochastic gradient descent. And what you will hear in the next lectures, you will hear, I'm sure you will hear about stochastic gradient descent, you will hear about online learning, you will hear about regularization, and you will recognize some of the simple models again, like the L2 regularized perceptron, called the support vector machine in this lecture. and logistic regression called the softmax in later models. You will hear about these models again. And so 2 ways of getting at nonlinear models. One is kernel machines, convex optimization. Another one, neural networks, non-convex optimization. And so if you look at the slides, I have, for each chapter, I have some papers that I think are useful and interesting. Maybe the paper that I want to recommend today is the last one here. It's by Leon Botou and Nossedal on optimization methods for large-scale machine learning. So that's a really nice introduction to convex optimization and non-convex optimization for machine learners. So something that you normally don't find in modern textbooks on neural networks and other things. It's the basics of the optimization routines that underlie the algorithm. Thank you very much. So do we have time for questions? No questions? Okay.
So I had a question about slide 112, or I can just say, so when we use a kernel trick, and you say when we can still use convex optimization, would it still converge to a global minimum, or does it depend on the kind of kernel that we use?
No, it will converge to a global minimum. That's the whole point, yeah?
Yeah, so then it would be assuming that the kernel is positive, definite. Let's say we use some kind of normalization, for example, a softmax where there is normalization to 1. Is this still a convex? Can I still use convex optimization to get global minimum?
Well, you have to tell me where you want to use this softmax.
For example, let's say the kernel mapping function is like a Gaussian kernel with sum to 1 normalization. So it's a softmax function.
Well, as long as the kernel is symmetric and positive definite, then the theorem will hold. You will have a feature representation implicitly that can be learned by linear optimization, by convex optimization. Yeah.
Okay. Yeah. Thank you.
Yeah, I'm sorry I took so. Yeah, please.
Thank you for a very nice lecture. Just a practical question. So how do kernel, like applying a higher dimensional kernel, scale computationally compared to alternative methods for introducing nonlinearity?
Well, they scale very poorly. So the standard techniques, you have to take the whole matrix of training data times training data. And the only way of making kernels efficient, or the idea of kernels efficient, is this here, where you use the randomization. It's even more efficient than neural networks, and you have to try it. Again, you have to do some handcrafting. You have to choose your randomization. What is it? What is it based on? Yeah. But this is a very nice technique. Yeah. Yeah.
Is this only a feed-forward network, or also like with backbone?
No. This is just, the network consists of an input layer, a randomization, which gives you a hidden layer, and then a nonlinear, a linear function from this layer. This is basically a perceptron. There's no multi-layer perceptron.
But I mean, do you have to backpropagate in order to have like different randomization?
No. Nothing is learned up to here, and here it's only one step. This is basically a perceptron. There is no backpropagation. There is no hidden layer. If there's no hidden layer, there's nothing to backpropagate. It's only one layer. It's an input and an output, and this is the weight.
But do you have like iteration and multiple time of randomization? No.
There is no backpropagation. It's just input layer, one hidden layer, and nothing is learned here, just the randomization. And then you do a linear model on this transformed input vector. And
Yeah,
of
but
course you do
you-
iterations, but iterations is something different than backpropagation. There is no hidden
Yeah,
layer.
so, but I mean, with the random, you only run random once or multiple times.
You choose, for each training run, you choose one randomization, because you have to make sure that each training datum is, of course, represented by the same random bin, by the same random signal in your Fourier transformation.
Yeah, but then it maybe like we need to have multiple time of the trainings and to make
Yeah,
sure that we
Sure,
have
we always
better
do multiple
organization.
training runs, but it's not backpropagation.
Yeah.
Yeah.
Yes, that's why I'm thinking it doesn't have. It only have like forward.
Yeah, maybe it's a misnomer to call this a neural network just because it has one hidden layer, but yeah, it is a one hidden layer network with where you only learn the output layer, which is a linear layer.
We should round off now and go for lunch, I think.
Okay.
But thank
yeah.
you very much.
Yeah, thank you.